Okay. One of the postulates of quantum mechanics stated that if you look at the Schrödinger equation, you can keep track of how a quantum system evolves with time. Like how much does it change with time? That creates a bit of an issue because that means we have to worry about time in everything we do. Through most of this class, what we're going to do is we're going to utilize this little trick to get to a time-independent Schrödinger equation. So one that doesn't evolve or change with time. Is that a good representation of reality for chemistry? Probably not. Why not? Yeah, exactly. Every aspect of what we do depends on time. You mix two molecules together, they're going to react. Something's gonna happen, hopefully. So in most cases, though, we really don't have to worry about time. If we do something called molecular dynamics simulations, and we can see how things change with time, especially quantum systems. That's something that we're going to really worry about more for lab. Before we do that, though, let's consider a one-dimensional, time-dependent Schrödinger equation. What's the generic Schrödinger equation all the time? Yep. H hat, psi, what comes out? Yep. Here, we're looking at the derivative with respect to time. So it shows how the quantum system changes with respect to time, and what does our wave function depend on? What variables? Yep, x, position, and time. So you can show, I really don't want to show this because it involves a lot of math and it eats up a lot of time to get to a pretty simple result. If you're very interested, I can give you lots of textbooks that do that and we can work through it together. It can be shown. Psi xt through the utilization of something called separation of variables. Okay, so we move to a wave function that is dependent on how many variables? From 2 to 1, yep. And then where does time in this thing? Yeah, up in this exponent. So time's up over here. Okay. What we're going to do is we're going to apply the time-dependent Schrödinger equation to this thing, and let's see what we get out. The way that you can do this is if you assume you have a standing wave. Do you guys know what I mean by a standing wave or not really? Okay. Let's look at a standing wave. Probably gonna have to lower these. Lily, can you lower that other one? Oh, I know. Come on, go down. I can't do this one. I'm just gonna pull it. Oh, that's why it's not working. I'm stuck on the chair. There we go. Okay. Should be okay. So we'll watch a video of a standing wave. I think I've shown this video to most of you in the past. Will, can you hit the lights for me? Thank you. Get out of here, darling. Okay, hopefully it doesn't destroy your eardrums. Yay, Valentine's Day ads. Okay, so what this guy is going to do, he's going to throw his phone into the guitar, and we're going to be able to see standing waves. So a lot of music is generated by standing waves depending on the instrument. And so you see how the string is moving, but it's not translating, right? It's oscillating, but it's not really going anywhere. The string stays on the guitar. If it didn't, guitar wouldn't work. Electrons can behave like standing waves, and we showed that also through the de Broglie equation. So we can even behave like standing waves given a certain area. So that's the idea behind what a standing wave is. Let's watch it go a little bit longer because it's cool. I like the lower notes so you can see it way better. So all a standing wave is something that is oscillating, but it's not moving. Overall, there's no net movement. So we can assume electrons do the same thing. So if we assume we're dealing with the standing wave, we can get that. We don't really have to deal with a mathematical proof to show this because you can use experiment to show that. There are mathematical proofs to go through that though. The big question then is H. What about H? How can we show that? There we go. We only get so much light through the year, so I'm letting more in. So what about the Hamiltonian operator? How can we deal with that? Okay. We got Hamiltonian operator operating on the time-dependent wave function. And we said that the Hamiltonian operator for the time-dependent wave function was this thing. Oops, not a negative. T that. So we got to do that operation on this guy. But what we can do is we can plug this thing into our equation. When we do that, we get just the portion that depends on x, and we get this e to the negative I t. Okay, ripped through a ton of mathematics really quick, sorry. This thing. How can we evaluate it? Or how could we simplify this? What can we pull out front? Yep. Why can we pull the wave function out? Yep, doesn't have a t in it. And then we just have to do the derivative I love these types of derivatives. They're easy, right? Let's leave this part alone. I take the derivative of this thing. What do I get out? Oh, yep, I less than I. There we go. Negative I e over h bar times what? Yeah. Okay. Let's take this stuff, let's combine stuff together. Get negative I squared h bar e divided by what? Yep. Times what else? Yep, it depends on x times, yeah. Simplify that part for me. That goes away, and we're left over with e times psi x. Oops. That thing. Okay. Now let's look at this. What does this part depend on? What? Yep. This bit over here. Can we separate these two portions? Yeah. We can separate them. So, what does the x portion give us? If we take that Hamiltonian. Or what did we show? Yep. And we've used this one a handful of times already, right? Cool. So what that shows us is we don't have to worry about time. We can move on from it. Okay.